So in this video, we're going to discuss improper integrals. So in particular, improper integrals come up when you're looking at a region that's unbounded in some sense, but you want to see whether or not the area that's in that region is actually finite, or more accurately perhaps, approaches a finite number. So look at the two particular cases that we might have for improper integrals illustrated by these figures. So over here, we've got a function that has a horizontal, pinching down to the x-axis here. It's got a horizontal asymptote of y equal to 0. So it's improper in the sense that the interval here is unbounded, right? We start off at 1, but we go off to infinity. So this is one type of improper integral where we've got an interval that's unbounded. Over here, we don't have that problem anymore. The interval that we're talking about here is from 0 to 2 on this picture. However, we see that the region's unbounded going up here because we've got a vertical asymptote. So we've got an unbounded function in this case that's causing the integral to be improper. So those are the two types of situations where we get improper integrals. However, we're going to handle them in a very, very similar way. All right, so like I mentioned before, the first one, we've got an unbounded interval. The second one, we've got an unbounded function. So either way, we're going to have to take a limit to try to evaluate these integrals. So let's do this by way of example. So let's first look at the integral from 1 to infinity of 1 over x dx. Certainly we see here that our interval is unbounded. We've not seen a case where we've got a limit of integration of infinity here. We've not seen that before this particular section. All right. So certainly if this is just any other number, in particular we'll be interested in real numbers that are bigger than 1 here, if we think about what that picture looked like on the previous slide, then we can certainly compute what this integral is. So again, here for a picture, here would be the function y equals 1 over x. Here all we're saying is, okay, instead of going off to infinity, let's just stop at some arbitrary b, if you will, somewhere bigger than 1, but obviously less than infinity. No matter what this b is, we can always compute what the integral is. Okay? Certainly all we need to do is, this is 1 over x is a nice continuous function on that interval from 1 to b. Again, as long as b here is bigger than 1, we're good. Do an antiderivative, plug in your endpoints. We get natural log of b for our integral. So what happens to this value as b gets larger and larger? Okay? So that's what we're really interested in, is what happens. So certainly this expression that we have, this natural log of b, gives us the area under y equals 1 over x, that's our function, on the interval from 1 to b. So to see what happens as b gets larger and larger, we're just going to take a limit of this expression. Well, certainly that limit goes off to infinity. So since the limit is infinite, that's telling us that we're getting an infinite amount of area underneath this curve. So the original integral that we had, the integral from 1 to infinity of 1 over x dx, we say that diverges. It doesn't approach a number. All right, so you might be thinking, okay, well, yeah, obviously this is an infinite amount of area because this curve never hits this axis. However, it may be the case that the curve comes down and pinches fast enough and makes it an actual finite area. It actually approaches a finite number. Think about it, if you just think about it numerically. Think about it if you had a sequence of decimals. Say you did 0.9, 0.99, 0.999, 0.9999, and so on. Certainly that's getting bigger every single time, but those decimals aren't ever going to get any bigger than 1. It's the same idea here. If this curve pinches down to the axis fast enough, the area can't get too big too fast. It ends up going to a finite number. So let's see if we have an example of when that happens. So let's just look at looks like a similar integral here, except I just changed the power to 3 rather than 1 on the x. So again, here's how we handle it. The improperness in this case is because we have an unbounded interval. So we're going to replace the infinity with a b, with some finite number b, and then we're going to take the limit as b goes to infinity. So we're going to evaluate the integral and then take the limit. Okay? Antiderivative for 1 over x cubed would be a negative 1 over 2x squared. Plug in your endpoints. We get 1 minus 1 over 2b squared. Now certainly in this case, as b goes to infinity, this term goes to 0. It's arbitrarily small here. This goes to 0, so this limit turns out to be 1. So in this case, this limit is finite limit. So we say the original integral converges, since the limit exists, and it converges to 1. Or again, more succinctly, we would just say that the integral equals 1. All right. Let's look at the unbounded function case, and to motivate why we have to do something different for unbounded functions, let's just consider this specific example. Integral from -2 to 1, 1 over x squared dx. All right, let's say we weren't paying attention. We've certainly done a lot of integration problems. We come up across the definite integral. Our steps are find an antiderivative, plug in the endpoints. Find an antiderivative, plug in the endpoints. That's what you're trained to do as soon as you learn the fundamental theorem of calculus. Okay, so let's just say we blindly apply the fundamental theorem of calculus. Okay, do an antiderivative. 1 over x squared, antiderivative, -1 over x. Plug in the endpoints. Plug in 1, plug in -2. Notice here we get a minus, a minus, a minus. So we'd still be subtracting here. -1 minus a half gives you -3 halves. Okay, yay, great. I got an answer. Wonderful. Except that this negative sign here should be setting off some extreme alarm bells in your brain. The reason is, let's go back up to the original integral. Not the interval, the function. Look at this function. It is squared on bottom, and the top is a 1. That means that this particular function is never negative. The graph of the function, if you think about the graph of y equals 1 over x squared, it's always above the x-axis. It's never negative. If the function is never negative, the integral can't be negative. Right? Remember, our first interpretation of the definite integral is area under a curve. If the function's above the x-axis, the area is positive. This function's above the x-axis, the definite integral should be positive, and it's not. So here, something went wrong. And what went wrong in this case is that to apply the fundamental theorem of calculus, we need a continuous integrand. And this function is not continuous at x equal to 0. It's not even defined at x equal to 0. It can't be continuous there. Okay. And in particular, if you look at the graph of 1 over x squared, you get a vertical asymptote. Okay. So we've got to handle it differently. So let's just look at that particular function, the 1 over x squared, at that asymptote piece, at the x equal to 0 piece, and let's see if we can handle it in a similar fashion to how we handled the unbounded interval case. All right, so the thing that's causing us the issue is what happens at 0. Well, if I replace 0 with anything bigger than 0, I certainly now have no continuity issues with 1 over x squared. So we'll replace it with a b, just like what we did for the case when we had an infinite limit of integration. We'll replace it with a b. Let the b get closer and closer to 0. Now technically it's getting closer and closer to 0 from the right hand side because these b's are bigger than 0, but we're approaching 0. So this is a right hand limit. Remember those one-sided limits back from first semester calculus. Okay. Then again, we'll, just like the previous case, we'll just evaluate an antiderivative and plug in the endpoints. Antiderivative, plug in the endpoints. So here you'll get a -1 and then a +1 over b, so we just wrote it the other direction. Now as b gets closer and closer to 0 from the right hand side, we're getting really small denominators, which means the fraction gets really big, and since we're coming in from the right, it's a really big positive number. This limit goes off to infinity. So just like in the previous problems, or the previous example, when the limit turned out to be infinity, we said that the integral diverged. So the integral diverges in this case. Now certainly they don't all diverge, otherwise there wouldn't be a lot of point in doing these exercises. So let's look at this one. Same problem. We got 1 over cube root of x is not defined at 0. Okay. So again, we'll have to take out the 0 and replace it with some number bigger than 0, calculate the integrals, and then take the limit as we approach 0. All right, so here this is x to the x to the -1/3 So its antiderivative would be, or an antiderivative would be 3/2 x to the 2/3. Plug in your endpoints. If you plug in 8, cube root of 8 is 2, squared is 4, over 2 is 2, times 3 is 6. And then put in b. That one's a little easier since there's not a lot of simplifying to do there. Again here, the limit is b approaches 0 from the right. Here, though, this is defined when b is 0, so I can just plug in 0 to evaluate the limit and get 6. So since this antiderivative, excuse me, since this limit existed, the integral exists, and we say it converges to 6. Or again, if you want to write it more succinctly, you could just say equals 6, like we've got this line of equal signs here. All right, so let's recap everything here. When you've got an unbounded interval with an infinity here, we replace that bad limit of integration with a real number, and then let that number go off to infinity. Now, we could have unbounded intervals, improper integral going in the other direction, where we have a negative infinity as our lower limit of integration. That's certainly possible, but you handle it in exactly the same way. You replace out the bad limit with a variable and let that variable go to the bad limit of integration. Likewise, if we have an infinite discontinuity for our function, if we have a vertical asymptote for our function at, say, x equal to c, again, that's what's causing our bad limit of integration. That's what's causing the improperness. So again, we replace that improperness with a variable and let that variable approach that bad limit of integration. In this case, we would be approaching from the left-hand side. Our c is our upper limit of integration, so we're coming from the low side for the b's. Or we could have c being the bad limit on the bottom. That was what we saw in the examples. The 0 was the lower limit of integration. So again, replace it and then take a limit. And in this case, the limit would be going from the right. It's also possible where you've got, I'll say, doubly improper integrals. So this one's doubly improper because both limits of integration are bad. They're both unbounded. So what you do in that case is you use your property of integrals that says that I can, basically, if I have a sum of two integrals with the same limit of integration, one as an upper limit, one as a lower limit, I can combine them together. Basically, we're just saying, okay, I can split it apart too. A can be any real number here that you choose. Usually, you'll choose a 1. Or excuse me, you'll choose a 0. Not choose a 1. Typically, you'll choose 0. It doesn't really matter. You can choose a 1. You can choose -7. It doesn't matter. For the case where you've got an infinite discontinuity and it's in the middle of your limits of integration, you need to split it up. Okay, so we would split it at the bad limit. In this case, it would split it at the discontinuity. All right. This one does matter. You want to split this at the discontinuity. And then you handle each individual integral like what we have listed up above. All right. The thing that's important to pay attention to for this particular case is that in both cases, absolutely, positively, both of them have to converge in order to say that the whole integral converges. Okay? If even one of them is infinity or minus infinity, you have to say diverges for the whole integral. Okay? So if you get one of them that turns out to be infinity, you don't even have to do the other one. And that's important. And it's especially important if you get something that looks like infinity minus infinity. That is not 0. Okay? Infinity minus infinity is undefined. So as soon as you get one that is diverges, the whole thing diverges.